Okay. Can you guys hear me all right? Can you guys like see my screen that I'm sharing on right now?
Yeah.
Yep.
All right. Sounds great. If you haven't had the chance, the sign-in link, the QR code for the sign-in link is right here. And yeah, let's get started. Okay. All right. So yeah, this last bullet point did not I thought I had it added, but I did not. But some quick announcements. We had the deadline for the fall quarter modules that was this past Sunday, and thank you to everybody who got your modules in on time. I know you guys were working pretty hard on that. The capstone projects were going to be released last week until a set of unfortunate circumstances. So we are going to push that to week 4 and beyond, or whenever we're back in person, but probably when the hardware DSP split happens. And then this current lecture is going to be the last lecture and module that everyone, like, no matter what your preference for DSP or hardware, needs to complete. Or you could just not do it. We won't track you down or anything. You get what you want out of rep. And then starting week 4, once this module is due, then that is when the official DSP hardware split is going to happen. And then so me and Victor are going to be in charge of separate lectures and separate modules. We'll have like different announcements channels and stuff, and then we'll just be going two separate paths. And then me and Victor are going to talk a little bit more about that at the end of this lecture, and then about what to expect. And Victor's gonna come. He's busy right now, but he'll come around halfway through this lecture. All right. So that being said, does anybody have any questions before we get into it? All right, sounds great. So, um, here's just a little bit of recap on what I covered in the previous CSP lecture because it's been like what, like 2 or 3 months. Um, so this is a diagram of the general just wrap system that we have. So everything here on the left side is going to be what's covered by the DSP side of wraps. That's going to be things like taking the bits that we generate from whatever message we want to send, and then we're going to map it to symbols. We use BPSK in wrap just because it's the simplest one, but so those symbols are going to look like just ones and negative ones in the in-phase component, and then nothing is going to be sent in the quadrature component. And then we're going to modulate that information onto a higher frequency carrier wave. The DSP, like my controllers, uses 1 megahertz for that carrier wave, and then it outputs it onto the digital analog converter, where it's going to be up converted to 1 megahertz from 1 megahertz to 27 megahertz. And then after that, it's going to go through the channel. It's going to be down converted, and then it's going to do all its like filtering, amplification stuff. And then the receiving microcontroller is also going to receive a 1 megahertz signal. And then that's where we do our demodulation that we covered in the last lecture. And this demodulation, this demodulation can be summarized by these equations. Oh, sorry, this is the modulation. So say we have our amplitude and phase modulated signal here, which is x of t, and we want to represent that in terms of the I and Q components because that makes it really easy to adjust the amplitude and phase because we can just adjust the amplitudes of individual sinusoids. One is a cosine and one is a sine. And then when we adjust the amplitudes of these ones, just like the strengths of them, and then add them together, then we get a properly phase and amplitude modulated signal. And that's what we mean by our I and Q representation. That is our in phase and quadrature. And then here's down below is just the process that we had that we outlined in the last lecture, where we do the simple mapping and then we do pulse shaping to go from our discrete symbols to an actual continuous waveform that doesn't interfere with like the future or previous symbols, and then it also like stays within its frequency bounds, so we're not interfering with any other frequency channels. And then we modulate that, and then we model any noise that we have, and then we do the demodulation. And then the demodulation, this last bit of review is just where we have x of t, and then if we multiply our incoming signal by a cosine, of the same phase and the same frequency, then we can actually then it creates a copy of like I of t at baseband, and then also two more copies at twice the frequency, or yeah, one copy of I of t at twice the frequency, another copy of Q of t at twice the frequency. And then when we low pass this, we can extract I of t, and then a very similar process for extracting the quadric component Q of t. Does that, I assume all of this sounds familiar, but if anybody wants me to like recap or like talk about a certain section again, yeah, just ask me now. All right. So the topic of today's lecture is twofold. Or the first part is going to be how do we actually efficiently implement the low pass function? Because in the MATLAB simulation for the previous assignment, we just used like the MATLAB magical low pass function, and then it did everything we wanted it to do. But I want to know, how do we actually implement this on our real-time embedded system in a way that lets us do our do our demodulation quick enough to like receive the messages, and it doesn't stall when we have a limited amount of RAM and processing power. So I'm going to be getting into a little like a very brief introduction about how digital filtering works and how we use it in RAP. And then, so that's going to be the first part of this lecture. And then the second part is going to be what happens when our phase and frequency uh, of the carrier wave we use to demodulate doesn't match what comes in as x of t, like our received waveform. What if that has a phase offset or a frequency offset? And I'm also going to talk about where those offsets come from. And you guys did see that at the end of the previous DSP assignment, where when we introduced like the channel modeling filter, that introduced I believe it was a 90-degree phase shift. So then we fixed that in the module with a very temporary fix, but I'm going to show you a very permanent fix. And then with these two steps, we are almost there to getting to knowing enough to implement this, like our entire theory into the microcontrollers for the real RAP system. So I'm going to start by getting off or going into digital filtering. And then I'm going to I know that a lot of the RAP students have like varying levels of experience with a lot of different topics. No one student knows everything they need to know about like the entire RAP system. So I'll try to go from the basic, like as basic as I can, and then build up from there. But if anybody needs me to go over something or explain something a different way, just stop me anytime. Okay. So yeah, I'm just going to start off very, very basics. Like, what is filtering? The general definition I can give is just it's some circuit or some method we can use to remove or like enhance or amplify certain frequency components from a signal. So I'm sure most of you know about like the frequency representation of our signals, or just the fact that like signals can have like low frequencies, middle frequencies, and higher frequencies. But what if we want to amplify or like remove parts of it? So this is just like a image I found off Google. The four main types of filters that we have are low pass filters, high pass filters, band pass, and notch. Low pass, it allows the lower frequencies to pass. High pass, it allows the high frequencies to pass. It's pretty self-explanatory. Band pass, if like the frequencies lie within a certain band, it allows them to pass. And the notch, it does the complete opposite of the bandpass filters. And I feel like most of you guys have seen this before, but I know not everybody has. So just bear with me. All right. And then if you guys have taken a systems and signals course, you would recognize what I'm showing you right now. But this is just how we model a lot of different systems within electrical engineering. So say I have like some sort of black box, like some function, it could be like a circuit, it could be anything, but I put an input into it and I get an output. And I want some mathematical way to represent the relationship between the output and the input. And there's two main ways we do this within electrical engineering. One is one is the version on the top where we have like our signals in the time domain. And then h of t, that's going to be our impulse response of our system. And if you don't know what that means, don't worry, you'll know it soon enough whenever you take 102. But I talked about convolution in the previous lecture, and this is really where convolution comes in handy because a lot of the signals and relationships in the time domain we can represent by convolving our input with some sort of impulse response, some sort of function, and then that's going to give us y of t, our output. So for example, like if I just have like a signal that's like this, and then I convolve it with just a straight up rectangle, it's going to smooth it out because the convolving here is kind of just like taking the average of the signal. So that's going to give me something similar to, I don't know, something like this. Um, so yeah, that's one way of modeling systems, and then the other way is going to be the bottom representation that I have here. This, just think of this as in the frequency domain. We can multiply this. A lot of times we just call this the transfer function, and then we can multiply the frequency domain representation of our input signal with the transfer function, and then we're going to get the the frequency representation of the output of the signal. And then, yeah, one property that we learn to know very well is that convolution in the time domain is going to be equivalent to multiplication in the frequency domain. All right, so now that that's out of the way, I'm going to actually just quickly go through a low pass filter example and then how we calculate the transfer function of that. So, okay, so we have this is just a very basic low pass filter. So I'm actually going to redraw this in a matter that you guys might be slightly more recognizable to you. So I'm going to draw it like this, and then here, and then let's say, all right, this should be a very quick audience participation. What did what did I just draw here?
Voltage divider.
Perfect. Thank you. And then does anyone know the equation for voltage divider?
VO would just be the ratio of like R2 over the total resistance times VN.
Yep. So we have let's see, we have V out equals what's it called? V out equals V in multiplied by R2 divided by R1 plus R2. Okay. So this should be something that you guys have seen before. Um yeah, this is like very basic circuits. But now it gets a little bit more complicated when we replace R2 with, say, a capacitor. And you guys might have seen in say if you've taken like ECE3 or one of the basic circuits classes that uh, or the concept of impedances for our basic circuit components. So the idea of impedance is kind of just think about it as like a frequency domain representation the of like resistances, and yeah, it's resistance in the frequency domain is the simplest way that I can put it. So I am putting the impedances for some of the the three basic circuit components. So now I can treat this voltage divider in the same way, but instead of R2, I'm going to replace it with the impedance of this capacitor. So now I have V out equals V in. Sorry, it's getting a little crowded here. Uh, I'm used to the whiteboard lectures where I have like much more space. So this is my first time giving a lecture on something like this. So just bear with me. But all right. So this is the equation that I have now, and then This I can actually, I'm gonna bring this over here. So yeah, I can then simplify this to um b in multiplied by 1 over 1 plus j c. All right, so um, all right, so yeah, now when I do this, I can relate v out to v in because remember what I was talking about earlier. We have this relationship between the input, and then the output, and then this is going to be the transfer function. So if I put v out over v in here, v out over v in, we're going to get 1 over 1 plus j. Yeah, get that right? Yeah. So here's it written out in fancy latex, but the concept that I kind of just wanted to drive home here was that the we have a way to represent the our circuits in term our circuits that we learn in like E3, 10, 110, in a familiar format that might look more akin to what you learn in 102, your basic systems and signals. So this is going to be our transfer function here, and then it's going to relate the output voltage to the input voltage, as and that's going to be a ratio determined by the resistances and the capacitances. And when my frequency goes up, that's going to be the omega term here. When the frequency goes up, the um yeah, if frequency increases, then this entire ratio will decrease, meaning that my output is going to be attenuated more. It's going to be lower. And then the lower my frequency is, the higher that ratio is. So then my output will not be attenuated as much. So then the actual, well, I don't have it memorized, but if if omega increases, then the gain or like the ratio between V out and V in, that's just going to it's going to have some decreasing. And then that is going to be what makes this a low pass filter because the lower frequencies are allowed to pass much more easily, where the higher frequencies are attenuated. And then I can actually calculate the I can actually calculate the magnitude and the phase of this frequency response. I won't worry too much about this, but the part that I want to drive home here is here. This is going to be this for this is just like for an example low pass filter on like the log scale. But all of the lower frequencies can pass through without attenuation. That's what 0 dB means. And then there's a certain frequency that's determined by the resistance and capacitance that determines like when we start to cut off the frequencies. And then there's also going to be a slight phase offset coming from that we can also calculate here by just taking the imaginary component and the real component of the transfer function, and then that's just going to be equivalent to like x and y, and then we just want to find the angle between them, so then we do inverse tan, and then we get this function. And then the last thing that I want to cover here is going to be the impulse response, because everything in the frequency domain, we can find a equivalent time domain version, equivalent time domain representation, and then this is actually going to be what the time domain representation is. So if us passing a input signal through this low pass filter is going to be equivalent to convolving this this impulse response with our input signal, and then that is going to low pass it. All right, did that make sense for everybody? I know a lot of this might be review, but yeah, does this sit well with everybody? All right. Okay. So that's analog filtering. It's done with it's done with certain components in the analog domain usually. But that is not what I'm here to talk about. Victor is actually going to go more in depth into analog filtering with analog circuit components if you choose the hardware track. But for now, this is kind of all we need to know for digital filtering. This just the fact that we have that like every filter we have has some sort of frequency response and it has our impulse response. The impulse response is the thing that matters most to us. But yeah, so we have analog filtering versus digital filtering. In digital filtering, we're doing everything digital. So instead of these components and dealing with like the actual electricity and like the physical circuits, we're going to do everything with numerical computations on digital signals. And if you've taken 113 or just dealt with like dealing with digital signals at all, you'll know that digital signals are discrete and they are not what's it called? They're not continuous. So this is just going to be like two equal or the digital representation of this signal. Just kidding. No, it's not. But anyways, um, when we take in our signals, like say through like an analog to digital converter, there it's just going to like look like an array within our software. And then if we have the sampling rate of the sampling rate for the data in that array, then we can hopefully reconstruct the analog stuff. But yeah, so here's just like a little bit of information about like digital filtering and like where you find it, anything with computers really. Um, but yeah, there are two main types of digital filtering methods, and or I guess just two types of digital filters that we have. One is called infinite impulse response filters, and the other is called finite impulse response filters. That's going usually they're abbreviated to IIR and FIR. And then you will probably see these a lot if you work in like the digital domain, especially in like the embedded computing domain, if you do anything with like communications or signal processing. But I'm first going to talk about infinite impulse responses. And as the name suggests, it's we're just dealing with an impulse response that is infinite. And this is kind of the same thing, the same idea as all of our analog filters, because say take our low pass filter that we had here and our impulse response, this goes on infinitely. Before time equals zero, it's all just zero, so we don't care about that. But it actually extends infinitely here. But using our analog components to implement this is no problem. But you can think about like if we try to do this digitally, we can't actually store like an infinite amount of samples because we have a limited amount of memory. So in practice, like, or yeah, we can't implement this like naively within our like within software. Um, but luckily, a lot of the times, like most impulse responses do tend to like fizzle out to zero. Yeah, do tend to fizzle out to zero as you move further away from like t equals zero. But like all analog filters are can be thought of as infinite IIR filters. And there actually are ways to implement IIR filters in in software, and then this involves keeping track of or having feedback to both use like like a set amount of your previous inputs as well as a set amount of your previous outputs. And in doing so, you can like manipulate the math equations to make it so that you don't actually need an infinite amount of memory. You can do this with like a set amount at some sacrifice of performance. So this is like what the actual block diagram for an IR filter looks like. These are slightly more complicated to design as an FIR filter because as you'll see in a second, FIR filters are actually pretty easy to like understand conceptually. Um, I won't cover IR filters any more than this. I just want to know that, like, I just want you guys to know that this is an option that you guys have out there. And then if you take a digital filtering class, in the future, you will definitely cover these very much in depth. But for RAP, we use FIR filters. But with IR filters, you can achieve like a lot faster of like roll off. You can like, AKA just like sharpness of your filter, with a lot less effort. But then these are also more unstable because just you can have like if your output is or you can if you have like zero as your input, you can still have like a non-zero output, unlike FIR filters. And then these are also slightly more difficult to design. But yeah, that's IR filters, but our main focus is going to be on FIR filters, finite impulse response. And as the name suggests, it's just if we cut off the impulse response at a certain point in time because it's fizzled out to zero, or we just don't really care, or we don't have the space to care. Um, and the actually, I'll cover this point later in the slides, but these are going to be the most common types of filters we have in the digital domain. And then we have just this is the mathematical representation of it. So if we have x, yeah, if we have x of n, yeah, here we're using n instead of t, just because this we're in the digital domain. But we're storing in our software the previous n minus one inputs. And then our impulse response, instead of just the regular continuous functions that we're used to, they're instead going to look like coefficients because they're just discrete points if we sample the impulse response at a constant rate. So then what that looks like here is like when you expand this function out, b is going to be the coefficients, x of n is going to be the nth input, the nth like piece of data in our array. So the output of the filter at the nth time slot is going to be the current input multiplied by this coefficient, and then the previous input n minus one multiplied by this coefficient, and then you keep going until you reach the last one multiplied by the last coefficient, and that's going to be represented here. This z minus or z to the negative one block, just think of this as like a delay block. Or sorry, not delay, or like going back one sample block. Um but yeah, and then this we can also just represent this as convolution. But a lot of times in the digital domain, we don't, if we're doing things iteratively and not trying to sample and not trying to filter the entire signal at once, like we do on paper, when we do like convolution, we can just represent this as just doing some multiplications with our coefficients and then adding them all together. And then, ooh, new sample comes in. We do the multiplications. We shift everything down, do the multiplications, add everything together. That's our new output sample. So that's why it's represented like this instead of convolution. But you can just, if you have the entire input signal already, then you can just convolve. Okay, and then here's how you actually, well, one method, kind of just more of like an easy way of thinking about it to design the FIR filters. You take a known filter shape, determine, well, don't worry about this line, but just take a known filter shape. For example, here, if this is going to be like my ideal low pass filter, and but oh yeah, and then the time domain representation of this is just going to be async. But then here we have kind of just like different implementations for a low pass filter, like different frequency responses, and that's going to lead to different time domain responses. But say I just start with this sync, right? That's going to be the impulse response for the filter that I want to replicate digitally. So then I'm going to discretize it. So I start with just like the continuous representation, and then I discretize it, so I kind of just like sample it at specific points at a constant rate. So then I'm left with like just these points. And then once I do that, I'm going to window it in the time domain, meaning I multiply it by some function that cuts off the points past a certain point. So let's just say like if it extended like shoot, if it extended like all the way here, I'm just gonna cut it off right here and cut it off right here. And then there's also a couple different windowing functions that you can use that maybe like it maybe weakens some of the points like towards the end, for example. So then like you can have like smoother transitions because like you might not want it to go like if we're in the middle of like if we're in the middle of the signal right here and then we drop it to zero right immediately, that might have some effects on the effectiveness of our filtering. So different windowing functions might lessen the impact. But you don't have to worry too much about that. Just know that they exist. And then now after that, you get a filter or you get the discrete points that represent your impulse response and then can convolve your input signal with this FIR filter. And I want to bring up a important property that we have for the Fourier transform, which is that the the shorter your signal is in the time domain, the longer or the more the bandwidth is in the frequency domain. And also that like sharp transitions in the time domain result in like larger bandwidth in the frequency domain. So I bring that up because if we say like cut our filter off here, that is going to make uh this frequency response like spread across more frequency because our time domain impulse response is sharper. Or versus like if we let this go on very long, the longer our impulse response goes, the closer it's going to look like this, like the ideal low pass filter. Um, so I bring a graphical representation of this is, well, here, this is just like the MATLAB code to generate a low pass FIR filter. Um, and then 15 15 is the order, like how many points we want our impulse response to be. And then we have our cutoff frequency, which is 1.5 megahertz, and then we give it the sample rate. And then here we're just extracting the coefficients of that filter, the coefficients meaning just the impulse response. So this is what I see. This is what the shape looks like when I have 15 coefficients, and this is what it looks like when I have 41 coefficients. Um, okay, I see. Oh, okay. Parth, do you want me to answer your question out loud or do you got it? Okay. Oh yeah, and if any of you guys have questions, stop me anytime or just drop it in the chat and I will and yeah, I'll see it. But so yeah, the
Hey Nat,
oh
I
yeah,
have a
what's
quick question.
uh-huh.
So on the previous page, when you're talking about designing the finite impulse response filter,
Yeah.
um, correct me if I'm wrong, but you're basically filtering an infinite impulse response filter through like windowing in order to create a finite impulse response filter, or like,
Yeah, that's how I want you guys to think about it. Like there's usually we just use like the MATLAB version of the filters, so we don't actually care about generating it ourselves. But let's just say we want to generate a filter representing like this ideal low pass filter, right? And then that's going to give us a sync function as the impulse response. So the first thing we do is we sample it. So I sample it here, here, here. And then we can't so we have our samples for the impulse response, but then we can't store an infinite amount of them. So we cut it off at some point, and then that's what our windowing function does. So it just like cut it off here, cut it off here. Did that answer your question?
yes, thank you.
Okay, yeah. All right. So, uh, yeah, the point that I want to drive home here was that the more coefficients you have for your filter, like the higher the order of the filter is. Oh, sorry, I forgot to cover this point. Uh, when we say like someone can say like, oh, and it's an N tap filter or a order N filter, that just means it's an FIR filter with N coefficients. So here this is going to be an order 15 filter. This is order 41. And you can see when we have 41 coefficients, it's the same it's the sh same shape as this. It's just it extends much further out, and the further it extends, the sharper our frequency response is. You can see like this is a very sharp corner here, whereas this is like kind of a weaker corner. Um, and yeah, okay. So, oh yeah, Bart.
Are the filter values stored beforehand?
Yes. So most of the time they're pre-calculated because there's it's really easy to just like calculate it in MATLAB, for example, or just like in your software and then just upload and store the coefficients of the filters just as an array in your systems. So then like the digital system doesn't have to worry about calculating this or do all of these optimizations. It just has the filter ahead of time. And it also lets us like switch out the filter at any time. So like I could click a button and my low pass filter in software suddenly becomes a high pass filter, which is another benefit of this.
Okay, thank you.
Yep. All right. Um, so I know most of you guys have finished the first DSP module, and in that module you actually used digital filtering twice. One is the low pass filter and one is the RRC filter. That's the root raised cosine filter. And then this is just some example code to generate a RRC filter. And it had a couple values that you can play with. One is going to be beta. That's just like how fast, like how sharp the roll off is. Um, one is SPS. That one is just like constant for your specific needs. Um, but the next one that you can play with is going to be the span. And that's what I want to bring attention to right now because this span, if you multiply it by SPS, which is the samples per second, that is going to give you the order of this FIR filter that this function generates. So here, if I have span of 5 and then SPS of 10, that is going to give me this pulse shape filter, which we then convolved with our received signal or our signal that we were about to transmit. And then you can see this actually has 50 points. That's just because the math that I explained earlier. And then if I have a span of 5, this is this is going to be the frequency response that it gives me. It's well, there's not we don't really have like a way to measure like how good it is right now, but we can just see like, oh, it's like it's got the shape we're looking for. It mostly keeps stuff within like its bounds. We see a little bit of curve here, a little bit of curve here, but it's fine. But then if I say have a span of say 50 right now, like this, we can see the order goes up to 500. It's same shape here, except it's like that this shape that we had is like concentrated all here, and we expand way farther out. And when we do this, we can see the frequency response is a lot cleaner. So this is just honestly probably unnecessary, but like say like if we care a lot about like we need to make sure we stay within these bounds, or we just like have a lot of space to play with, then why not go for a higher order for our filters? So yeah, that is the content that I had for digital filtering. A little bit of context is I think in the wrap system last year, our order for the RRC filter was around like 400 just because it had to span like multiple symbols. But then our order for the low pass filters that we actually used were like 11. But then we tested out like trying to get away with like as low as 5 because like these the lower the order of the filters are, the more computation we can save. So we are just trying to figure out like what's the minimum amount of space for the filters that we need in order to optimize but have it still work. So that's something that we played around with a lot in DSP R&D last year. And yeah, the first part of well, one of the parts of this upcoming assignment that are released tonight is going to be replacing your low pass filters in the previous assignment with low pass filters that you generate using MATLAB and then like actually convolving it yourself instead of using the magical MATLAB low pass function. But yeah, I'll I'll give everybody well, I haven't been lecturing for too long, but I need a water break, so I'll give everyone like a 5 minute break. But before that, did anybody have any questions? All right, cool. So yeah, 5 minute break. I'll come back around 6:50, and then I'll get into the second half of this lecture. Okay, so that was a introduction for digital filtering and how we use it in the RAP system and how you guys will influence it in this upcoming assignment. And then the rest of this lecture is dedicated to the problem that I introduced at the end of the previous assignment, which was how do we handle phase and frequency offsets that might arise during this whole process when during our demodulation it requires us to have the same phase and frequency for the sinusoids that we demodulate with. So before I get into it, before I get into like deriving the algorithm, I wanted to ask a question. This is kind of just a little bit of context for how our algorithm works, but if the like say we have two signals. Um, and then there's like they might be offset in some way. But my question for you guys is like if the phase of the two signals always matches 100%, like we have a way to just like constantly adjust the phase in our signals, can there or just like if the two phases match, can there be a mismatch in frequency?
I wouldn't think so.
Yeah. And do you have like any explanation why? It could just be like a sentence or just like because it makes sense.
Yeah, I think like the concept of phase to me really only makes sense if two things are operating at the same frequency. And if they're out of frequency, then like they can't be said to be in phase or out of phase.
Yeah, exactly. If two things have different frequencies, then the second like you move to the next time point, they're obviously going to be out of phase just because they're moving at different speeds. And then that leads me to the next question. If frequency always matches, can there be a mismatch in phase?
Yes.
All right. Yeah, easy. Um, Yeah, so that's just because like say like the two frequencies could be exactly the same, but if they start at a different phase offset, then they're always going to be offset by that exact amount. Um, but the intuition I wanted to build here was that remember in the previous assignment when we corrected our or the offset by just changing our sinusoids during demodulation by to match that phase offset. So the the received signal had some sort of offset, and then we just matched the offset during demodulation. So say if we can do that for any sort of phase offset, then we're automatically correcting for a frequency offset as long as we can always keep that phase aligned. And then here's just a little bit about um, where these phase and frequency offsets come from. One is just straight up the transmission and propagation delay. It's going to take time for like electrical signals to travel between the microcontrollers and like through our hardware. And then also time for the wireless signals to transmit and then get received. So that's going to introduce some sort of phase offset. And then there's also slight hardware differences that could cause a phase and frequency offset. Like say if the crystal on one microcontroller is like running at like 480 hertz or something like that's our clock speed, but because of like very slight hardware differences, it could be running at like 48.01 like megahertz. Or sorry, I meant to say megahertz. Um and then my other microcontroller could be running at like 479.99. But that very slight offset can like throw our communication off wildly after a certain amount of time. And then we also have stuff like the Doppler effect. So like say I'm walking around with my rap transmitter, like typing in messages. I'm in my fancy Cybertruck while I'm doing this. And then the Cybertruck is barreling towards an unsuspecting holder of the rap receiver, Prame here. So then the Doppler effect that we learned in our physics classes means the frequency of this transmission that we get as as observed by Prame is going to be a higher frequency. So that's just a little bit about like where phase and frequency offsets can come from. Um, so this is kind of this page is dedicated to deriving the result that we saw in the previous assignment. Like, why do we actually care about about this phase and frequency offset? What happens when we have this phase and frequency offset and then do our naive demodulation? So I'm actually going to derive the result that we see and then like explain why we saw the things that we saw in the assignment. So like before we had x of t and that's going to be the equal to the in phase component. And then cosine omega t. Okay, so this is just what we know. Let's just call this like I'm just gonna put an S there for cent. And then so once we receive this, or to do our demodulation, let's say that the regular demodulation equation that we had was just we multiply things by two, and then we apply a low pass filter to the result of what was it like x of t, and then multiply by I believe it was cosine of W naught t. That's what we got in the previous lecture. But let's just say that um, there's some phase offset. So just for simplicity, I'm going to add that phase offset to here. I'm going to represent it by, oh shoot, what Greek letter is that? I think that's phi. I'm just going to call it phi if it's not. Um, so that's the phase offset here is just represented by phi, and then um, we can equate this to what's it called? To if we expand this out, then we get I of t cosine of omega t, and then cosine of like t plus I minus q of t sine omega t. Yeah, I'm only gonna do this derivation once, so just bear with me here. Uh, okay. So when we have this, this is going to be, I can already tell this is going to be kind of an annoying result, so I'm going to break this up into parts. I'm just going to call this A. So if I only look at this section, which is just the in-phase component multiplied by the cosine with the phase offset, then I'm going to, that's going to be equal to uh, I of t. Gonna write this down and then explain a little bit about where I got it from in a bit, but let me just make sure I have it written down correctly first.
Sorry, is A just the I of t portion, or does it also include the Q of t?
Oh, sorry. A is just this. Yeah, just the I of t portion. Just so I can break it up. I'm not going to do this whole derivation because we'll see that it simplifies pretty quickly. But to break, I broke up the I broke up this the cosine omega plus the phase offset into I used what's it called? I used the trig rule of if you have cosine and then two things, it's going to equal the cosine of of the multiplication of those two things. Uh, and then you subtract the sine of the multiplication of those two things. We're going to be using a lot of trig rules up here coming up. So I'm just gonna put this to the side here. Um, so then now I can simplify this even more by just saying, oh, I have two cosines multiplied together. I can use one more trig rule. That was if I multiply two cosines instead, um, then I'm going to get 1/2 multiplied by the uh, cosine of the differences of those two components added with the cosine of the sum of them. And then this is a rule that we used in the previous lecture. But when I have these two cosines multiplied together, that's going to give me uh t cosine da da da, and that's going to be 1/2 plus 1/2. Um, oh wait, sorry, not 1/2. Just regular 1 plus cosine of, and then the frequency, and then I'm going to get. Wait, I wrote this backwards. This should be. Sorry about that. This should be like this. Um, yeah. So then when I do that, I'm going to get this, which is something that I can low pass out, but I'm going to still have that factor of cosine and then phi. And then I still have this one, and then like in the previous lecture, that is going to simplify to um what was it? Sine of two. So yeah, I actually may have made an algebra mistake here, but I'll correct it before I post the slides. But the point that I want to drive home here is that oh, never mind. This actually, sorry. The point that I want to drive home here is that once I low pass filter this, I'm going to get I of t cosine of phi. So me having this phase offset is going to introduce this term of cosine phi into my result when I try to get I of t. And then if I do this one, the bottom part of this, um, if you do the yeah, if you calculate that out, that and then take the low pass of it, that is going to give you negative negative q of t, and then it's going to have sine of the sine of phi. Um, you'll never have to use this. You'll never have to use this derivation, but this just gives you some good context for why things happen the way they do. So this is going to just give us like when we demodulate, it's going to give us I uh descent multiplied by cosine phi minus q cent of t sine phi. And then we can do the same thing for q or for the quadratic component. I won't bore you guys with that, but I will revise this after this lecture so I can post some accurate notes. But these are the results that you get when we have a phase difference. And then this is kind of what we saw during the assignment. Uh, so whatever the phase difference is, if we have the same frequency, then it's just going to shift our entire constellation diagram by a little bit because all this means is like some of our quadrature component is leaking into our received in-phase component, and some of our in-phase component is leaking into our quadrature component. So that is going to be what causes this rotation that we have. And then so that's when we have a phase mismatch. When we have a frequency mismatch, I'm not going to derive this whole thing because we can use the same results that we got before, but let's just say like our received one is just 2 times the result when you low pass uh, I of t, and then multiply by cosine of. So we're going to get our original frequency plus whatever frequency offset that we have multiplied by t. Um, yeah, multiplied by t, and then we can, oh yeah, q of t sine of omega naught t cosine of omega naught plus the difference in the frequencies multiplied by t. So here, the difference is we have a difference of delta omega times t, just the change of frequency. But if we treat that the exact same as phi here, then we're going to get a very similar result. But the result that we're going to get is instead of phi being here, we're just going to get delta omega, the difference in frequencies. And then as time goes on, this phase offset is going to change. So the amount that the quadrature component leaks into the in-phase component changes by a set amount, like that's dependent on time. So we're going to get this sort of spinning effect. And like as we keep demodulating, it's just going to keep spinning, and go around forever. And this is, well, the phase offset here, we can reason about like how it should be rotated back, but this one is just completely gone. We don't know what's what. So that is what happens when we have our phase and frequency differences. Um, and this is what you guys would have observed in the previous assignment. So our first intuition for like how we can solve this might be like, oh, what if we just use an FFT on the receiver side to calculate what the actual like received frequency is? Like after all the Doppler effects, like after everything, just like what frequency do we see from our perspective on the receiver side? And while this works to give a rough estimate to find the frequency, it would only work if the frequency is constant. And if the frequency changes at all, then this is kind of useless because you'd have to keep calculating the FFT. And the time complexity of the FFT is not very forgiving. And we already have a rough estimate of the frequency. That's just going to be the frequency that we originally sent it as. Because say we sent it at 1 megahertz from the transmitter microcontroller, and then at it come at the receiver microcontroller at like 101 megahertz. So we expect it to be within the ballpark of what we sent it in, with like only like a little bit of shifting. So we are going to take a different approach. Oh, and also this doesn't really help us do work with the phase, like find out the phase information. So um, the remainder of this lecture is going to be posing this as a optimization problem that we can apply some sort of algorithm that like iteratively like looks at and tries to determine the phase, so that we can properly demodulate. So let's just say we had, or this is just what we've been doing so far, which is this is going to be from the receiver's perspective. What we see is x of t, which is just like the whatever we receive at the analog to digital converter after everything. And then we can mathematically represent this as I of t at the center. So that's just going to be like 1 or -1. And then multiply by oh yeah, so and then this is assuming now that we're in BPSK just to make these calculations easier. So we don't care about the culture component anymore when we're calculating this. So we're just looking at the in phase component. And then this is going to be writing on our 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 cosine. This is going to be our carrier wave with some sort of phase offset. But instead of this being omega naught, instead of it being like our perfect 1 megahertz, it could be like 101 megahertz. It could be like 99 megahertz. We don't actually know. So we're just calling that the received omega instead, omega r. Um, and our job is to try and deal with the fact that we don't know this and we don't know this. So if we expand this out, we can actually. Right, this might seem kind of pointless right now, but let's just say we add add in the cent frequencies. This is just going to be like 100 megahertz in our example, and then this is also just going to be this is also just going to be 100 megahertz. So if we add and subtract the same amount, it's going to be equivalent. But now I want to take all of this and just lump it into one term. So that's going to be, shoot, what is that Greek letter? Does anybody know?
I think that's just capital phi.
Cap. Wait, so this is phi? Wait, what's this one?
I think that's also phi, but let me check.
Oh shit. I may have wanted to choose better ones. Okay, so
The one of them's capitalized, one of them's lowercase.
man, all right. Well, we're not using this anymore after this slide, so big phi. All right, so now we're gonna let big phi. That's going to be dependent on t. So it's just going to be like some changing thing, like changing phase offset throughout time that we're going to use to model the difference in frequency between our sent frequency and our received frequency, as well as the whatever phase offset might come from like propagation delay or anything else. So now all we have is just now we can represent this in terms of the send frequency, which is just 100 megahertz, and then all we need to do is determine this. That's a little bit harder, easier said than done. But now this simplifies this equation more so that like we have one more known, and then we just have this much bigger unknown that we have to track. But if you remember from the previous assignment, all we need to do is just match the phase offset of what's coming in. And if we constantly do that, that lets us get rid of both phase and frequency offsets from the result that we calculated at the start of this section. So yeah, so when we have this is just going to be the big mystery, and we just want to constantly match it. It's going to be constantly changing through like as we move our wrap system around and due to external factors. So we're just going to in out when we do our demodulation, if we add in our own phase offset, we determine this one. If we add in our own phase offset and have some way of matching this with big phi, then we're going to properly demodulate. So when we do this demodulation, we already recalculated this result earlier. Well, this result looks a little bit different because we have offsets in both sides, but if you calculate it out, we're going to get this, which just tells us that if theta and big phi match, then they cancel each other out. So then this is going to be zero. The value of cosine at 0 is just going to be 1. So we're just going to get the regular, just like 1 or -1 as our symbol, as our I component that we get from sending. And then Q component, we don't really care about this too much now, but it gets a similar result. So our goal in this optimization problem is to minimize the difference, the absolute value of the difference between theta and big phi, or put another way, we can just think of it as we want to maximize the received I component. Like whenever we have a sample, we know it should be either 1 or -1. So if it looks like point 0.7 or something, then we know like, oh, we're a little bit off. Some of our Q component leaked in because we're not getting the maximum value for I. Because remember, we like assuming the amplitudes stay constant between I and Q, if we don't get a straight up one, that means we've rotated a little bit and some of our Q component has leaked in. So yeah, now I'm going to introduce, oh yeah, Parsa.
Yeah, and I just had a couple questions. So one is that when we were doing the previous DSP module, we didn't have a Q component at all. So is that going to be how we're going to move forward with wrap, or are we going to add in a Q component at some point?
Um, we're going to utilize the Q component in the upcoming algorithm, but in terms of like the actual communication and whether we're utilizing the Q component for like sending data, that might be one of the options to like extend wrap in Spring by like evolving from like the BPSK to QPSK or like actually using the Q component like send data more efficiently. But as of the wrap system right now and for the assignments, we will be sticking with BPSK as we hammer in these last few concepts.
Okay, so then if we're sticking with BPSK right now, then this method of letting big phi and theta be the same will work because you'll get a cosine of 0. But then if you did want to have a Q component that carried some meaning, would this method not work anymore because you would get a sine of 0, so you wouldn't get any information there?
Yeah, so remember how I guess when I did the original derivations of these, I included both the I and Q component, assuming that I was sending data through I and Q. But then when deriving this, I kind of just like there's there's no Q component. I kind of just ignored it because I know we're doing BPSK. The algorithm will look slightly differently if you have I and Q, but it's essentially just like you're just adding in another term. And then your error function is going to look slightly differently. But this algorithm and everything I talk about from here on, I'm simplifying it for BPSK, but is easily extended for QPSK or like other communication schemes.
Okay, perfect. Thank you.
Yep. All right. Yeah. If anybody else has any questions, all right. So yeah. So the goal, like when you do an optimization problem, you always have to have like some sort of goal. Um, and then my goal here is let's just say I want to maximize the received I component. So this is just a little bit about like how we approach problems like these a lot within like numerical computing and like say just machine learning and stuff like that. So the idea behind gradient descent, which is a term I'm sure most of you have heard like one way or another, but you just define some sort of loss function or cost function. They kind of mean the same thing. Um, and then let's just call that J. So this is kind of like if you do PID and then you have like an error term, right? That's like a similar concept. So you want to minimize this. Um, so the best way to like when you're in like a math class like calculus, the best way to find a minimum of something or maximum is to take the derivative. And then when you take the derivative and look at it at a certain point, it's whether that derivative is positive or negative tells you whether the function is like going up or going down when you move forward in time. So, like, say, like, if I want to minimize something and my derivative is negative, I'm just going to go in whatever direction leads to me having a smaller value at that function, and that derivative is going to tell us that. And then if we're in 3D, then that derivative becomes a gradient. Gradient is just a derivative with multiple variables instead of just one. So then we can like move in like a 3D or a 4D plane and just like keep updating our parameters, um, and then calculate what our loss is at that new point. So let's just say I start, what's a good color for this? I start right here, and then my derivative oh yeah, this is just a graph like for J, and then J is just some function that has W await as an input. So here, the derivative with respect to W is going to be some negative value, right? So then that means like, okay, if I keep going forward, like if I increase W, then J should decrease because that's how derivatives work. So then I'm gonna go here and then like, oh, okay, it worked. My derivative is still negative, so I'm just gonna keep going. Okay, my derivative is like getting slightly closer to zero, but it's still negative here, here, here. And then once I'm at here, that means the my derivative is zero. So then I know that I am at a minimum. Is this like the absolute minimum in my entire system? I don't know. I don't care. But I found a minimum, and this is good enough for me in this circumstance. Um, and so yeah, if I want to model this mathematically, then I just have, if W is my input, then I have like my new value of W is going to be equal to my old value of W. Um, this can either be plus or minus. It really depends how you define it. It doesn't matter. But and then I say like for example, this example subtract. I subtract the derivative or the value that I get from the derivative multiplied by some constant factor. If I and the higher this constant factor is, that in machine learning is oftentimes called the learning rate. That's just going to be like how big of a step I could take. Like if I had a really big alpha, then I could jump all the way to here. But that also means like I might just like get stuck bouncing between here and here and here and here because my steps aren't small enough. But if I have a very small alpha, then I it's going to take me like a lot of steps to get to my eventual destination. Okay, so that I don't know how actually yeah, I don't know how many of you guys are familiar with gradient descent. I'm sure you guys have heard it at some point, but that's just the general idea. Does this make sense before we go forward? All right, cool. Okay. Yeah, so I'm not going to go to the next slide yet because that has, well, the answers for this next part. But I am now going to use this concept and derive our next step. So we let's just say our goal right now is to sorry. Let's say our goal right now is to maximize the um maximize our received I component. Give me 1 second to flip to the correct page in my notes. Okay, so yeah, if I want to maximize I, then let's just say I'm gonna check here. Oh, sorry, this is maximize the I component squared because this I component could be positive or negative. So squaring it is just an easy way for us to take out that negative. And then we'll see why this is especially handy in a second. But let's just say I have a cost function, and then that cost function we represent as j, and that is just going to be equal to what we just talked about. I talked about minimizing our cost function in the previous slide, but if we maximize like we can also maximize it and then just like put a negative. The direction doesn't actually matter. So here I'm just going to use this one as our cost function. And then this, if you remember, is going to be equal to the result that we've become very familiar with. We're going to low pass filter and then get x of t cosine of omega t plus the phase offset that we create. And then this phase offset that we create, which is theta of t, that is going to be our one input into this function. So we want to find how this cost function changes when I change theta of t. Like if I wiggle it around, will my cost function increase or decrease? And that is where the beauty of just like taking the derivative comes from. So if
Sorry, can I
I,
ask a quick question?
oh yeah, go ahead.
Right, so on like the next slide where you have it typed out, you have a cosine omega s and no t plus theta t. So is there a t or is there no t?
Uh, that is a mistake. I believe there's a T there. Sorry about
Yeah.
that. Um, but yeah, so it should be omega of T. And then that makes sense because we always are like this is going to be like the sinusoid that we demodulate with. And then that is always going to have just like the constant frequency and then the time component. And we'll multiply that together, that gives us the phase of the sinusoid. So yeah. So if I take the derivative of the cost function here, um, with respect to theta, we are going to get, well, okay, let's look at this. The first component for the derivative, like we have a square on the outside. So let's just start with the chain rule. Easy enough. So we have two, two times the low pass filter of x of t cosine of omega t plus theta of t. Oh, let me add this back in. Okay, so yeah, that is the. Oh, actually, since there's this two on the outside, I'm just gonna sneak that back in here. Okay. And then now that's just going to be multiplied by the derivative of whatever's on the inside, right? So d theta 2 times low pass filter x of t cosine omega t plus theta of t. All right. Um, and this is something you may or may not know from your classes, like your what's it called? Systems and signals classes. But the low pass filter function is going to be a linear function. So that makes our job here a lot easier because we don't need to worry about like finding the derivative of that because we can kind of just like the same way we can take this 2 on the outside and just move it, we can also take the low pass filter on the outside. So this is going to equal I don't want to draw this out again, so I'm just gonna copy this. I'll also clean this up while I'm at it. Okay. Um, so now we can kind of just move this on the outside. Uh, low pass filter. Um, but now we have the the derivative with respect to theta of this whole term. And then if we do that, we see okay, x of t that well, the inputs to that doesn't have any theta. So that one we can also just move out. We don't care about it. So then this ends up actually being very simple. It's just the derivative of a cosine. We know we know how to do that. That's easy. So I'll duplicate this one more time. Um, but I assume you guys already know what this result is going to be. So this is just going to be if I replace this x of t multiplied by a negative sign because that's the derivative of a cosine. We get a negative sign. Um, Now my question to you guys is, um, wait, did I get? Oh, okay. Anyways, my question to you guys is does this form for this one and this one look familiar at all? Maybe? Yes? No? Anybody?
I and Q, but like with coefficients.
Thank you, James. But yeah, so let's just look at this. So I have 2 times the low pass filter of x of t times cosine of something. Um, and then this, which is just 2 times the x of t negative sine, and then that. So that all of these is going to be equal to, yeah, just wait, actually, no, this one. This is just going to be equal to the received I component and the received Q component, which we already have during this demodulation because that's what we're starting with, right? So this is just going to be the received I component, and this is just going to be the received Q component. So this suddenly this like daunting equation became a lot more familiar to us. And then this is actually going to be the error term that we update our guess for theta by. That being dj over d theta equals uh was it 4 times the I component times the Q component. The This doesn't actually matter. I'll just call it, yeah. Okay, sure. Um, so now we have an update term, and then that is all we needed for this because we've successfully found the derivative of our cost function with respect to our input parameter being theta, the phase of the sinusoids that we demodulate with. And then we can update this dynamically by just saying like what is it? Theta new equals theta old um plus uh some alpha times the received I component times the received Q component. All right. And then I'm going to do a little bit more of derivation here just so we can see some more of the motivation of like why this actually works. So when we have like the received I component and the received Q component, if I expand this out, then I'm going to get IS of cosine, cosine big phi uh minus this. This is something that we had in a previous slide. And then I'm going to multiply this by, well, since we have no Q component here, this is going to end up being just the amount of the I component that leaks in to our Q component. Big phi times theta of t. Yeah, okay. And then this is actually going to simplify to we have a sine multiplied by a cosine, so that should immediately make us think of one of our trig identities that we know and love. So we have negative sine of 2 times the whatever's within these sines and cosines. Luckily, it's the same thing. So this minus this. And then the I'm pulling out something you probably haven't used in a while, but the first order Taylor series approximation. Um, First order meaning we don't really care too much about the sign part. We just want to know like the very basic estimation. That is going to equal the negative of just the straight up difference between the big phi and then this. So back when remember back when we were determining like what our cost function would be, we want to either minimize this or minimize this one or maximize this one. Well, in the process of maximizing the received in-phase component, we are actually if we maximize J, that is the same thing as minimizing this one because the bigger this one gets, like the since it's negative, that's equivalent to minimizing it if this term gets higher. Um, so where was I going with this? Oh yeah. And then we can also see that just like the further our phase or the phase difference between theta and big phi is, the larger the update is going to be. And then that is the result that we calculated here. Or this is just like formalized in fancy LaTeX because my handwriting on this tablet is pretty bad. But now we're starting to wrap up. This is going to be like add the error function that we use, but now I want to see like is does this actually make sense? Like what are we actually doing here? So let's just say like we're demodulating like iteratively. So we have a point that like lands somewhere here, right? So the I component and the Q component, let's just say like a d dj over d theta. That's going to be positive because we're in the positive quadrant. So we can make that so that our phase offset brings us here. So we're going to adjust the phase, and then we can have it so that like if we land somewhere within here, it's going to bring us closer to this one. So that whether that's increasing our theta or decreasing it, it doesn't really matter the direction. It's either one or the other. You just try both. But yeah, and then if we're in this quadrant, quadrant 4, then our result is going to be negative. So then uh opposite result of this, opposite direction, we're gonna go towards here. But then the opposite thing happens when we cross over here. That's actually going to bring us here and then here. So the second we cross over this one, this is kind of like you can think of it as like an unstable equilibrium point. We're never gonna stick around here for long. We're always going to be drawn towards the equilibrium points of here, and this is where our received I component is maximized. That was a lot of words. Does this derivation and like our motivations here make sense? All right, cool. We are almost there. There's just one last thing that I want to cover. Oh shoot, since this is a PDF, it's not doing the fancy animation. Hold on. Um, so yeah, I guess I don't need to write anything else. So yeah, the yeah, this is reference to the micromouse slides, but if you have taken PID or done micromouse or just like dealt with control systems at all, you've probably heard of PID. That is a proportional integral derivative controller, and it helps us track some certain things. So say I'm a car trying to catch up to like some specific point. The farther away I am from it, that we can call that our error term. So like say if I'm like very far away, I want to run faster. So that's just what our proportional term does for us. It says the farther away we are from our goal, the harder we're going to try to get to that goal. And then the integral term just means that like, oh, if I've been running for a while using like my proportional term, but I still haven't caught up, let me give myself a little bit more of a boost. And that is very conveniently represented as the integral term within this. If we integrate the error, then it's going to make our strength stronger if our error is like steady state. And then derivative, this just prevents overshoots and oscillations. And when we combine all of them, that's going to be our PID controller, and that lets us like accurately track a moving target. So we can see on the right, this is the red one is like when our proportional term isn't, or yeah, our proportional term is like okay, but we can't properly catch up because we don't have any integral and it's a moving target. The yellow term here, that's it dampens our thing and reduces some of the overshoots and oscillations. So you can see it's a lot more steady than the red one, but it still doesn't catch up. And then we only actually catch up with the green one because you can see it's like slowly accumulating errors, and then it's like giving it the strength to fully catch up to the moving target. So yeah, that is going to be what, oh yeah, that's PID. Um, I need this to move to the next slide. Okay, I'm just gonna move back here. All right. So, I bring this up because our phase for this, like the phase offset that we get for our received signal, that is going to be like constantly changing. And then when it's constantly changing, maybe this isn't enough because this kind of just represents a proportional term, if we think about it in PID settings. So this alpha could be thought of as the P coefficient, and we're only doing it based off of our distance from our perceived goal. So if we combine PID with what we're talking about now, we can use the derivative of the error function as our error term within a PID setting, and then we can have three different coefficients representing the proportional, integral, and derivative coefficients in a regular PID system, and then use this term to update our guess for the theta, the phase, instead of just this one. And so this will allow us to handle, like if there's a frequency offset, then there's going to be a steady state error. Our goal is always going to be moving. So this is going to help us like get to that goal as soon as possible and stick there. So then this is going to be our final block diagram. This is the last content slide I have for you guys tonight. But yeah, so this is going to be the entire like process that I've defined here. That is actually called a Costas loop. And it happens when it can be done in hardware or software. For these assignments, we do it in software, and in the current RAP system. But say like we take our signal. It's just like hot off the ADC. We don't know what anything means yet. So then we're going to demodulate one sample, just a singular sample, with our generated cosines and sines. This is just like as normal, right? And then from that we do our like we low pass it, so then we get our received I and Q components, but then we take the results of these, like the I and Q components, we multiply them together, and that's our error term. So then this loop filter updates, like takes in this error term and then updates our guess for uh theta. So then if we keep updating our guess for theta, we're eventually going to like lock on to what the best value for theta is, even if it's like changing. We're just going to keep tracking it. And then the closer we get to that, the better this demodulation gets. And then we can just keep going and demodulate the entire signal continuously. And as time goes on, our guess for theta is going to be more and more correct, and we're going to get better values for the in phase and quadrature components. And that is how a Costas loop works. Does anybody have any questions? Did I lose anybody?
I just had a quick question, Nat.
Yeah.
Um, so is the alpha value the one that we're tuning, um, like in the system, or is it just set to one thing? And then, does that make sense?
Yeah, so when we're testing this, like in this next module, the first part is going to be like implementing like the low pass filters, but the second part is going to be implementing Costas loop. So you guys are going to like iteratively test, like similar to like if you took EE3 like with the cars, you're going to iteratively test what the best values for the proportional, integral, and derivative coefficients are. And then once those are chosen, you just set them in the system and forget about it. And that's what we did in the RAP system last year. We like did simulations in MATLAB to like record what the data looks like, and then like figured out what the optimal values for all the coefficients were, and then saved that into our microcontrollers, and then it does demodulation with the Costas loop from there.
Thank you.
Yep. So yeah, this is what we use in our microcontrollers for the RAP system. And I think it's pretty cool just because it solves three problems at once, which is the phase offset, frequency offset, and it does the demodulation for us. We get our I components and our Q components. So then the last thing that we really need to solve is just this I component is just gonna look like this, or it's gonna look like this, and we need to figure out where to sample it. And there's like some other timing algorithms that like figure out like, oh, okay, I sample it here, sample it here, sample it here. That's what we're gonna cover in the next lecture. But this is by far the most significant step that we take in order to being able to implement this in real time on our systems. But yeah, if there's no more questions, me and Victor are going to talk a little bit about what to expect for the rest of Wrap once we split off into our DSP side and our hardware side. Yeah. Any last questions? All right. Cool. So, all right, you know what, Victor, I'm gonna let you talk first. I need a break.
Yeah, for sure. Hey guys, it's me again. I didn't really have any like crazy photos to show of what the hardware split would be, because I'm trying to pilot something slightly new this year. Photos on the right, you see one of them is something unrelated really to rap in terms of the thing that you see on the oscilloscope. And the top photo is just this thing that I was working on as part of my R&D. Um, if that works, I could think about providing an extra lecture for you guys to learn about that, but that's TBD. Anyways, so what is the hardware split? So you guys have probably had some hands-on experience, or not hands-on experience, but like simulation experience now on how to make like a buffer and an amplifier system, theoretically, and an oscillator. Um, by the way, shout out to everyone that's completed all of the hardware modules and the software module so far. Um, what hardware is going to go into more is the whole process of upconversion. Now we basically uh, learned most of the building blocks. Mixers is probably one of the last major building blocks that we'll learn. That's in the next lecture, and then we'll talk about filters. We'll do a little bit of network analysis. Maybe we'll learn something about S parameters, Z parameters, how to measure those things with your nano VNAs, what different types of like characterization methods for your networks, like insertion loss, conversion loss, signal to noise ratio, all of those things will be covered. And then finally, like all of the things that we've been brushing under the rug in terms of hardware, all the non-idealities and non-linearities will be exposed to you guys so that if you guys want to go on and do R&D, you'll have a better idea of like some of the other like real world issues that we might face, and not everything is like ideal in the simulation. So what's planned for RAP in terms of the capstone would be uh, if you guys have seen the wrap system, it's built in terms of like PCB modules. So what you guys would do is you guys would design your own PCB module to replace in the wrap system, and then you guys can test it by connecting it up to the actual wrap system to see if it would function. If it functions, then you've completed the capstone and it'll work. But if it like doesn't, there's more troubleshooting. The idea was here is that you can infinitely expand. So you can start off with one module and replace only one module on the board. And if you finish that and you want to keep going, you can keep designing more and more modules until if you really are up for it, the entire wrap system you can make from ground up by just building each module separately. With that, you'll get experience with interfacing with the test equipment, such as the oscilloscopes, the spectrum analyzers. I will work with you guys to like learn more about how to use those things, especially also the nano VNA, how to calibrate it, how to use it, how to get information out of it. You'll learn more about that. Yeah, so you'll interface TLDR is your interface test equipment. You'll learn how to make your own PCB, design your own PCB. You'll troubleshoot, and hopefully you'll have a working module that you can replace, or not replace, but you can test on our current system. Yeah. Any questions? All right.
All right, cool. Yeah, thanks, Victor. And now a little bit about what's left for DSP. After this, like this upcoming assignment, you're going to simulate in MATLAB like how the Costas loop algorithm works, as well as implementing the digital filters. And then all we have left for the MATLAB simulations is frame synchronization, which is like how do we determine what like when we have actually let me explain timing recovery first. That's just like how we can look at the I and Q components that we demodulate and then determine like, oh, okay, this is a sample, because from the microcontroller's perspective, it's just a bunch of numbers that came in. This is like just determining how we extract the bits from that. And then frame synchronization is going to be how we know what bits like correspond to the start and end of a message. And then I'll combine that with channel coding, which is just when we can send certain messages that correspond to different bits, and then we can specifically create these messages in a way to handle like a lot of different things and like bit errors. Um, and then yeah, just creating our messages in a way that minimizes errors. Um, but then the actual fun part, in my opinion, is just the ability to actually like start implementing all of these stuff that we do in MATLAB onto our actual embedded microcontrollers. I'm definitely like an embedded programming type of person, so this is like what drew me to rap in the first place. But one of the assignments this quarter, this is just think of this as like your winter capstone. That's going to be I'm going to give you a microcontroller, and then you're going to implement the transmitter side of wrap yourself in C on these microcontrollers, because the transmitter side is like a lot simpler than the receiver side because you don't need any of these like fancy like tracking algorithms, but it's going to give you a good experience, like a lot of embedded experience and like how we actually do these things in the real world. So that's what I'm gonna have all of you guys do if you're interested in the DSP side of rap. I talked to Professor Ian Roberts last quarter, and then last year, and then at that time he agreed that he could give a advanced topics lecture for just like communication systems because that's what his main research is in. So I'm going to schedule that either late this quarter or early next quarter. But then past that, once we get like these last couple assignments out of the way, then we're going to jump into the R&D portion, which is just where I'll introduce to you guys like the current state of the wrap system and then like potential improvements, and like how it works. And then you guys are going to implement like new topics and like different optimizations to improve the wrap system. And that will be I'm going to give you guys a couple options, but if you have anything specific you want to do, you will have the choice to. For example, last year, one of our students was very interested in the topic of channel coding, and last year Rap didn't. Last year was the first year that Rap actually worked. So there was a lot of space to make certain improvements and like implement certain features. So the student was interested in channel coding, so he actually implemented channel coding onto the Rap system, and now it's used in the Rap system whenever we demo it. So I'll create a list of R&D topics. Some of them could just be like expanding it to like use QPSK instead, or like OFDM, or to handle different noise algorithms or channel modeling. There's a lot of different things we can do, but essentially it's just a all hands on deck effort to create the next generation wrap system. But yeah, so that is kind of what you can expect for the rest of the year. This is again going to be the last lecture and assignment that pertains to all the students. Um, I'm gonna release it sometime tonight along with the lecture recording, and it will be due at the end of week 4, and that's when the official split will happen.
And Nat, do you wanna make it, or how do you wanna track who's in which track, or do you want to just let them decide?
Um, we can honestly
Like,
just
do you
send
want
out
a
a Google
form?
form, yeah.
You want to do a form? Okay.
Yeah, and then some students have expressed interest in doing both tracks. If you do want to do both tracks, like it's definitely possible. Um, it- just keep in mind that there will be separate assignments for both of them. But yeah, just talk to us. We'll leave it as an option on the form. And yeah, that'll happen sometime in week 4 once this assignment is due. Yeah. Any last questions before we wrap up?
Can I ask a question to Victor about the hardware split? So like the capstone, is that for